All right, let's try and clear a few things up for exercise 3K. Hopefully you can see this. We got a general quadratic in its expanded form, its most general form. Most of our work is looking at turning this into a factorized or a completed square form. And the reason we spend so much time doing this is because the different forms tell us something about the graph. When it looks like this, we know that the y-intercept is 12. If we can factorize it, then we know that the intercepts are -6 and -2. If we can complete the square, we know that the turning point is -4, -4, somewhere there. And we put a lot of time and effort into perfecting the techniques to get from here to here, or from here to here, or from there to there, and round and round and round we go, and turning those forms into the graph. And you've done all the work. What 3K is about is, if I tell you something about the graph, if I give you this information, can you work backwards to produce one of these? Usually not all of them, just one of them. If I tell you the intercepts, could you produce this? If I told you the turning point, could you come up with this? And if I told you a bunch of random information about the graph, could you come up with this? So that's the kind of the why we're doing the work. And that'll be the same throughout the year. We'll do a bunch of algebra. We'll learn about different families of graphs and what they look like. And then after we become good at it, we'll practice, well, here's a graph. Could you reverse engineer that into what the equation would be? The way the book presents this, it talks about families of graphs. And we'll have a look at question 2 to make the point. We've got a parabola. Here's a very general. We don't know what A is. We don't know what B is, but it goes through 4 as a y-intercept. So as a family, what they have in common is that there's a y-intercept of 4. And I've set up a little graphing calculator to illustrate this. This is the question as it is in the book. And A and B are numbers that could be anything. There's infinite graphs in this family. It's an enormous family. It's so big, it goes on forever. And depending what A and B are, I mean, that's just changing A. There goes A. Could be anything. But for every value of A, there's infinite values of B as well. I'm only going from -10 to 10. But if we move that, there's a whole nother infinity over here. It's a massive family. But what they have in common is they all go through -4 there. -4, through +4. Apologies if I said -4 twice. If we have a look at the question, what it says is, okay, for this family, if perhaps it happens to have a turning point here, then what's the value of that graph? And using my sliders, well, that's on the wrong side, so put it up that way, move it over that way, make it a bit. This is hard work. Trying to decide what dilated all the way over there. Keep dilating. You get the drift. There's a particular combination of A and B that would put the turning point right there. And once we lock in that X and Y value, that would be two degrees of freedom that would lock in A and B. It's a very common math methods idea that there's this whole family of graphs, and we'll slowly give you more information about, okay, so it goes through here, and then there's this other relationship, and then, okay, it goes through this point, and you drip fed the information until you've got enough to lock in all the variables. So I've had a crack at working this question out. Originally, it talks about having a family of graphs that has a y-intercept of +4, and we've seen that there's infinite of those. And later on in the question, it says, well, what if one of these family members has a turning point on the x-axis at -4? And any time that we're told about a turning point of a quadratic graph, we should be trying to build the equation in turning point form. It's the most straightforward, it makes sense. If it's in terms of, if you've had lots of practice graphing in turning point form, you know that a parabola that has been moved 4 in the negative x direction has an h value of +4. And if it hasn't been moved up or down, it has a k value of 0. And so we can kind of summarize that. It looks like this: y equals, might be dilated, x minus 4 moved across 4, and then nothing because it's not moved up or down. And this is the sort of thing we see in example 44, which is, I think, is confusing you a little bit, but we'll get back to it. So that's putting in the information that we get from the turning point. We're not sure if it's dilated or not. I can tell you it is, because from -4 over to 0, a distance of 4, we would expect for a parabola, when you go across 4, to go up 16. Y equals x squared. That's the idea. When you go across 4, you go up 16. But that doesn't happen. So there must be some sort of dilating of the growth. In order for us to find out what that number is, that A, and to prove it, we take this number, which is 0, 4, when x is 0, y equals 4, and we put that in the equation. Right, we found this out so far. When x is 0, y equals 4. Write that out. Do the maths. -4 squared is 16. 16a is 4. Divide by the 16. A is 1 over 4. So that's the equation of the parabola. If we were going to get it in general form, expand the brackets, x squared minus 8x plus 16, a quarter of that, x squared plus 2x plus 4. X squared plus 2x plus 4 is probably the final answer to that question. Let's go and have a look at example 44, which you're a little bit annoyed about. We're going to have a look. What's happening here is, in our notes, we've given you 3 basic quadratic equation forms that you can work from. There they are there. Oh, missed it. Like this. So we've got general form, where you can build 3 equations and put them into your calculator and get them to work it out. If you're told about the turning point and you've got one other extra clue, you can use this. We've just done one on this video. Or you might be told about the intercepts and you'll need an extra point, and you can work that out the same way we've just kind of done it. These are the 3 basic forms that we talk about in the course. Over on example 44, they have forms of the equation that are different to that. Where are we? Yeah, let's have a look at 40. Yeah, so 44 we're talking about, weren't we? All right, so we've got a parabola here. The turning point is labelled, pardon me, as 0, 0, and we have this other one. So what, in the way I've presented it, we would say, go write it out, a minus h squared plus k, where when you look at it, h equals 0 and k equals 0, so you don't really need those numbers, which is why when you look at the working out, they haven't got, if you imagine there's a bracket plus h, but h is 0, and then plus a k, and k is 0 on the end. That's why this looks like this. I mean, it looks like they've randomly selected it's x squared, but it might be dilated. Yeah, it's an x squared graph, but it might be dilated. Let's look at it. Y equals x squared, kind of the original parabola goes through the turning point, but we don't know if there's a dilation or not. We can guess that there is, because when you go across 2, you should go up 4, whereas this one, when you go across 2, you go up 5, so there's some sort of dilation going on there. This one here, it's shifted up, but it's not shifted left or right. So the h value, y equals x minus h, square that, and then add k. There won't be an h value, but there will be a k value, and the k value should be 3. When we look at B, there it is. It's not shifted left or right. We don't have an h value, but this k on the end, they've used the c, which seems a bit random, but that's the idea. And then they take the other point that's listed and put it in and solve for c, and then we get an answer, which is what we've been talking about. C, here we go. So we've got, I see 2 intercepts and I see another point, which is some information. So one of the brackets would be x minus 0, which is just x, and the other bracket would be x minus 3. When we come down, they've put it in the form as x minus 3 and x minus 0. They've kind of skipped the 0 bit and just called it x. And the dilation factor out the front, there's that. Go through, do the maths, put in the other points, and come up with the equation. Another one where you get the turning point, you get the other random point, so that because there's a dilation, a translation right, and there's a translation up, they list both. Go use the other information, put it in, get it all, and then you can expand it out to general form. So that's where those come from. They're not completely random. They do fit with the way we've kind of presented the information in the PowerPoint. It's just that when you put it in, there might be zeros, and the book has kind of left those out, where if we would do that work before we arrive at this idea. Your question about example 40, it might be easiest for you and I to catch up in class about that. Are we coming? Hold on. I would have a look at that question myself. Where are we? Here we are. And working backwards. So it's got an intercept of 2. There's infinite parabolas. They could be on one side going up and down. They could be wide. They could be thin. It could be on the other side. It could be wide. It could be thin. My initial idea was, well, let's look at the axis of symmetry, which is kind of either here